Hello students, welcome to the class of Control System 1. I am Priyanjali Mukherjee, Assistant Professor of Electrical Engineering Department of Narula Institute of Technology. In this class, we will discuss on the concepts of Bode plot. This video lecture consists the introduction to the Bode plot, the scale on the Bode plot, and the Bode plot of some basic factors such as the constant gain, the derivative factor, the integral factor, the first order factor in the denominator and the numerator, and how to plot the magnitude plot on semi-log graph paper or the slope on the semi-log graph paper. So, in the frequency response analysis, we have learned that in the previous videos that it has so many advantages with respect to the time domain analysis. The frequency response of the linear time invariant system is independent on the amplitude and the phase of the input test signal. The design and parameter adjustment of the closed loop system for specified closed loop performance can be easily carried out in frequency domain rather than the time domain, whereas the effect of noise disturbance and the parameter variations in frequency domain can be easily visualized. And there is a correlation between the time domain and the frequency domain specifications. So, the time domain performance of a linear system can be easily predicted using the frequency domain specifications. The transfer function of the system can be obtained from the frequency response. That's why, due to these advantages, we can use the frequency response plots which can be represented in various forms depending upon the linear scale, logarithmic scale and the coordinate system. So, there are different type of frequency response plot, among which we have already discussed with the Nyquist plot or the polar plot. So, now we are going to learn the Bode plot. So, Bode plot is the graph of a frequency response of a system. The magnitude and the phase of the frequency response against the frequency can be plotted directly on linear scale. But the main disadvantage with the linear plot is cumbersome computations. So, to avoid this, it is convenient to plot the magnitude and the phase shift curves with a logarithmic scale. And this plotting of magnitude and phase shift with a logarithmic scale is known as the Bode plot. Now, this Bode plot gives us the information more clearly than the corresponding linear plot. The information compressed near the origin in a linear plot can be easily visualized in the Bode plot, as the logarithmic frequency is magnified near origin in case of the Bode plot. So, the Bode plot consists two plots. One is the magnitude plot and another is the phase plot. So, the magnitude plot of the sinusoidal transfer function against the logarithmic frequency, that means the frequency on the log scale. And the second plot, that is the phase plot, is the plot of the phase angle against the logarithmic frequency. And in generally, the magnitude of sinusoidal transfer function, that is the mod of Gj omega, can be calculated in the decibel unit. Now, the graphical addition of individual terms Bode plot gives us the complete Bode plot. Now, the scale used in the Bode plot. So, there are two types of plots. One is the magnitude plot and another one is the phase angle plot. So, in magnitude plot of the open loop transfer function is in decibel, that is expressed in the dB. And to convert this into dB, we are using that 20 log mod of Gj omega or Hj omega. And the phase angle of the open loop transfer function is expressed in degrees. And for the logarithmic plot, the base of the logarithm has to be considered as a 10. And the next one is the frequency of the Bode plot that are plotted against the logarithmic frequency axis. And every frequency axis represents a power of 10 times of the previous value, and that is known as the decade. The term decade comes from the Latin word that means 10, and decade is an increase in frequency by 10 times. So, the slope, which is actually the ratio of y-axis by x-axis, can be measured in dB per decade. That means the decibel per decade. So, if we consider an example, the frequency band between suppose 0.3 and 3 radian per second is known as the decade. Now, in the Bode magnitude plot measures the system input-output ratio in the dB unit. So, the Bode plot measures the phase shift in the degree, but also the radians can be used, but in this video lecture, we have plotted against the degree. Now, to convert the decibel, we have to multiply it with 20 log. So, suppose form is there A by B, then to convert it into decibel, we will multiply it with 20 log A by B, or it can be written as 20 log C. Now, the Bode plot of some basic factors. Now, the Bode plot, the magnitude is in logarithmic scale. So, the two cascaded systems is addition of Bode plots of the individual systems, and any transfer function can be factored in terms of some basic factors. And if we know the Bode plot of the basic factors, then these Bode plots can be graphically added to get the Bode plot of the given transfer function. So, there are total 8 basic factors. Among those, in this video lecture, we will consider the constant gain k, the integral factor, that means a pole at origin, the derivative factor, that is the zero at origin, the first order factor in the denominator, that means pole on the real axis, the first order factor in the numerator, that is a zero on the real axis, and the first order factors with repeated poles or the zeros. So, let's start with the Bode plot of basic factors such as constant gain. So, for this constant gain, I am considering here Gs equal to K, which is actually the open loop transfer function. So, the sinusoidal transfer function will be G of J omega. So, we will put J omega instead of S. So, G of J omega will be K. So, the magnitude in dB can be written as 20 log K, whereas the phase angle is the consider the first case when the k is equal to 1. So if we put 20 log k, here k is equal to 1, then the log 1 becomes 0. So the magnitude becomes 0. So that's why when the k is 1, then the magnitude is 0 dB. And the phase angle, that is always 0 degree. So the Bode plot when k is equal to 1 is the horizontal line at 0 dB. That is this axis, this real axis. And the upper half is the magnitude plot and the lower half is the phase plot. And this magnitude plot we are plotting against the log omega and the magnitude is dB. So this unit is decibel and this is the logarithmic scale of omega and unit is radian per second. So for k value that is equal to 1, we have got the horizontal line at the level 0 dB. Next, consider the case when k is greater than 1. So when the k is greater than 1, suppose we can consider the value that is equal to any value greater than 1, that may be 2, that may be 3, that may be 4 or any value a. So it becomes 20 log a or 20 log that value. So it will be a positive constant and the angle will be again 0. So the Bode plot is the horizontal line that is parallel to this real axis at that value level. So if we consider that k is equal to 2, so we have to find the value of log 2 and then 20 log 2, and that will be the value of this portion. So the Bode plot will be the horizontal straight line at that level in dB. So let us consider the third case. So in third case, we have considered that k is greater than 0 but less than 1. So in this case, if we consider the value of k, then we will get the magnitude as a negative constant and the angle remains same, that is again 0 degree. So the Bode plot is the horizontal straight line at the level in dB and the magnitude plot of the k is the horizontal straight line having that magnitude and the phase plot that is also a straight line passing through 0 degree for all values of omega. So that's why I have written here 0 to infinite. So whatever the value of omega is, the phase angle is always a straight line through 0 in degree. So keep it in mind that magnitude axis is in dB and the phase angle is always expressed in the degree unit. So this is the complete Bode plot of the basic factor constant gain, where we have considered three cases. This is the value for k equal to 1. This is the magnitude plot for k greater than 1. And here we have considered the value of k that is greater than 0 but less than 1. And this is the phase plot with the omega value that is 0 to infinite. So whatever the value of omega is, the phase angle is always 0 degree. So let us take another example of Bode plot of a common factor, that is the derivative factor. So the derivative factor is considered here. Gs is equal to S. So the Bode plot of a derivative factor means a 0 is located at the origin. So here S means a 0 is located in the origin. So here Gs is equal to S, that is the open loop transfer function. So in G of j omega, it becomes only j omega. And j omega can be represented in rectangular form, that is equal to 0 plus j omega. Whereas in the polar form, it will be omega into and phase angle is 90 degree. So here also we can see this magnitude is depending upon the omega. So if we vary the omega values, then we will get the different magnitude curves. But the phase angle is only 90 degree. So the phase angle curve will only the straight line with irrespective of the value of omega. So it will always 90 degree, that is the parallel line and the straight line with respect to this reference 0 degree line. So now we will consider three different cases according to the value of omega. So let's take the omega equal to 0.1 radian per second. So when omega equal to 0.1 radian per second, and if we put that value in the magnitude plot, then it becomes 20 log 0.1, and 20 log 0.1 means it is minus 20 dB. So if we consider that the omega is varying from here, so here it is value is 0.1, then per decade, that is 1, 10, 100 like this. So at 0.1, the magnitude is minus 20 dB. So that's why at 0.1, this is minus 20 dB. Here one confusion may come that here it is written 0 and 0.1. Actually this 0 represents this y-axis where it is in dB. So it is, this point is 0 dB and this one is plus 20 dB, this one is minus 20 dB. And the omega at this line is 0.1, and then per decade it is changing like this 0, 1. That means in between this 0 to 1 there are only one decade, and again 1 to 10 there is another decade, and 10 to 100 there will be another decade. So at omega equal to 0.1, the value of the magnitude is minus 20 dB. And next, when the omega value is 1 radian per second, so we will put the 20 log 1 dB. Now 20 log 1, as value of log 1 is 0, so 20 log 1 becomes 0 dB. So the magnitude will be 0 dB at the omega value equal to 1 radian per second. Next, we are varying the value at 10 radian per second. So if you put 20 log 10, so it becomes plus 20. So at 10, the magnitude is plus 20. Therefore, the plot is actually a straight line that is passing through the 0 dB at 1 radian per second, and the slope is 20 dB per decade, and the phase plot, that is the horizontal straight line at 90 degree. So this one is the Bode plot of derivative factor, and here I have considered that only one zero is located at the origin. Now it is possible that there are multiple zeros at the origin. So if we consider there are two zeros, then this GS will be actually S square. That means S to the power n. So we can vary it from S to S to the power n. So if you know the Bode plot of one derivative factor, then easily we can find out the Bode plot of multiple derivative factor. So let us consider it is GS is equal to S to the power n. That means n number of zeros are located at the origin. And then what will happen? So the g of j omega will be j omega whole to the power n, and the magnitude in decibel it will be multiplied by n, that is n into 20 log omega dB, and the phase angle, that is also multiplied by n, that is n into 90 degree. So what does it mean? That means if there are two zeros at origin, so the power will be S square and the magnitude will be 2 into 20 log omega. That means actually it is 40 log omega, and the phase angle will be 2 into 90, that means 180 degree. And like this, we can easily find out the n number of zeros when located at origin. Then we can find out the Bode plot of the multiple derivative factors by just multiplying n in the magnitude and the phase angle. So let us take another example, that is the Bode plot of the integral factor. So integral factor means there is a pole at origin. Now when the pole is located at origin, I have considered the open loop transfer function as Gs equal to 1 by S. So the sinusoidal function becomes 1 by j omega. So we can multiply both sides by j, that means minus j divided by omega. So in rectangular form, we can write this equation as 0 minus of j by omega, and in the polar coordinate form, we can write 1 by omega into angle of minus 90 degree. Whenever the S, that means when it is at denominator, then it represents the pole. So when a pole is located, then for each pole, the angle contribution will be in minus. And if this is 0, then the angle contribution will be in plus. So here it is located at denominator, that means it is a pole. So the angle contribution will be minus 90 degree. And the magnitude in dB will be minus 20 log omega. Actually, it is 20 log minus 1 by omega, and due to that 1 by omega, it becomes minus 20 log omega. So now the phase angle is minus 90 degree. That means it is not depending upon the value of omega. So whatever the value of omega is taken, the phase angle plot will be a straight line that will be passing through minus 90 degree, just like this. So the Bode plot, this is the phase plot of the 1 by S, that is always minus 90 degree straight line passing through minus 90 degree, that is the parallel of this 0 degree and minus 180 degree. And it is always remain same irrespective of the values of omega. Now what will be the magnitude plot? So to plot the magnitude, we will consider the different values of omega. So first consider omega is 0.1. I have started with 0.1 because in this x-axis I have considered that omega is first varying from 0.1 and then consider the 1 decade, that is 0.1 is multiplied by 1, so it becomes 1, and multiplied by 10, so it becomes 1. Then this one is multiplied by 10, so it becomes 10, and next this 10 is multiplied by 10, so it is 100, like this. So this distance is representing 1 decade, and in this omega is varying from 0.1 to 1000 or 100 or so on. And in the y-axis, it is represented the magnitude in dB, and this is the reference 0 dB line, and from that there is 20 dB plus 40 dB, this one is minus 20 dB and this one is minus 40 dB. So when we start to vary the value of omega from 0.1, then at 0.1, if we put the value of omega 0. over here, that means this magnitude relation, then it becomes 20 dB. So it is plus 20 dB, that's why at 0.1 the dB is 20 and the graph will be starting from this point. So next we are considering the value at 1. Omega is 1. So when omega will be 1, so it means it will be 0 dB. So the slope is going downwards and at 1 it is at 0 dB. And the next one is omega equal to 10 radian per second. So when omega equal to 10 radian per second, so that means 20 log of 10, so it becomes minus 20 degree, because log of 10 is here 1 and we are considering all the base equal to 10. So at omega is equal to 10 radian per second, the magnitude becomes minus 20 degree. So this one is, if we consider this value, so omega is 10 over here, and at this value the magnitude is minus 20 dB. So this is the slope with minus 20 dB per decade, and this is the magnitude plot. That means plot in dB versus log omega, that is frequency in logarithmic scale, is actually a straight line having the slope of minus 20 dB per decade passing through the 0 dB line when the omega value is equal to 1. Now how to draw the slope? Why slope is dB per decade? So what is the relation between the straight line? Expression of straight line is y is equal to m of x, and m is the slope and m is the ratio of, that is the y axis by the x. So here y axis is represented by dB and the x axis is represented by decade in logarithmic scale. So the unit becomes 20 dB minus 20 dB per decade. So the unit is dB per decade. And the range of frequency from any omega to 10 omega, that means 10 times increase, which I have said in earlier slide, that is the 10 times increase is called a decade. So initially, if omega is equal to 1, then the range from omega equal to 1 to omega equal to 10 is a decade. Initially, if we consider omega is equal to 0.5, then the range of 0.5 to 0.5 into 10, that is equal to 5, is a decade. That means 0.1 to 1 is a decade, 1 to 10 is a decade, 10 to 100 is a decade, 100 to 1000 will be a decade. So this is the decade concept. And for a decade frequency range, the magnitude is changed from 0 dB to minus 20 dB. That means here for 1 to 10, here the magnitude is changing from 0 dB to minus 20 dB. So we can say the slope of this straight line is minus 20 dB per decade. So this is the complete magnitude plot, and phase plot is independent the value of the omega, and it has a constant value of minus 90 degree throughout the all frequencies of the omega. So it is a Bode plot of a single integral factor, that is a single pole at origin. Now what will happen if there are multiple poles are located at origin? So multiple poles mean 1 by s to the power n, and if it is s to the power n, then g of j omega, it becomes 1 by j omega whole to the power n, or the mod of g j omega is actually minus 20, it will be multiplied by n here, minus 20 into n into log omega. So if n is equal to 2, it becomes minus 40 log omega. If n is equal to 3, then it will be 60 minus 60 log omega. If n is equal to 4, that will be minus 80 log omega, and so on. And for the phase angle, that phase angle is minus 90 degree for single pole. So it will be minus of n into 90 degree. So for two number of poles at origin, the angle will be minus 2 into 90, that is the minus 180 degree. If it is 3, that the power of s is equal to 3, so it will be minus 3 into 90, that is minus 270 degree, and so on. So if we can draw the Bode plot of a single integral factor, then by multiplying it with the n, that is the multiple roots or the multiple poles at origin, easily we can find out the Bode plot. So let us next example. So this one is the Bode plot of first order factor that is located at the denominator. So when it is located at denominator, so it is considered as 1 by 1 plus s tau. So the sinusoidal function becomes 1 by 1 plus j omega tau. So the mod of g j omega becomes in dB, it becomes 20 log 1 by root over of 1 plus omega square tau square or omega square t square. And if we solve this, then we will get that is equal to, as a square root is there, so it is actually to the power half. So it becomes minus 10 log 1 plus omega square t square. Now here there are, so it is summation of two terms, and the phase angle becomes minus of tan inverse omega t. So now consider the cases. So first consider the when the omega t is less than 1. That means omega is less than 1 by tau. So here it is the low frequency portion. Then the omega tau or the omega t is considered assumed to be negligible, and the magnitude becomes the 0 dB. And when omega t is equal to 0.1, so if we put 0.1 over here, then the magnitude becomes 0 dB, because it becomes minus 20 log of 1. So this is the first case. So the phase angle at the low frequency range, when omega is less than 1 by tau, then this magnitude is 0 dB. And the phase angle is 0 degree. So the phase, this is a phase plot, and this is 0.1. Omega is varying from 0.1, then per decade, that is 1, 10, like this. So at 0.1, the magnitude is 0 dB from 0 to 1, and here the angle is 0 degree. Now the omega is starting to increase. So what will happen if omega is greater than 1? That is the high frequency portion. So when omega t is greater than 1 or omega is greater than 1 by tau, then the magnitude is minus 20 log omega t. That means 1 is assumed to be negligible here. So it becomes minus 20 log omega t. And omega t is equal to 1, that means omega equal to 1 by t. And at omega t equal to 1 or omega equal to 1 by t, if we put the value, then the magnitude becomes 0 dB. Whereas when the value of omega t is equal to 10, that means omega equal to 10 by t, or the magnitude becomes minus 20 dB. So for here 0.1, the magnitude is 0 dB, but at 1, the magnitude has changed from 0 dB to minus 0 dB to minus 20 dB per decade slope. And at omega t is equal to 10 or omega equal to 10 divided by t, the magnitude becomes minus 20 dB. And what about the phase angle? So for the phase angle, when omega t is very less, then the phase angle is 0 degree, and at omega equal to 1 by tau, that is this 1 radian per second, it becomes minus 45 degree, whereas when it is larger, then it goes to minus 90 degree at the value of 10. So this is the plot of magnitude, and this is the plot of the phase angle. And at omega equal to 1 by tau or 1 by t, the magnitude is minus 20 log omega t, and phase angle is minus 45 degree. That means we can say that at this point omega equal to 1 by tau or omega t is equal to 1, here two straight lines will make this point, and this meeting point is known as the corner frequency of the system. Or we can say from the corner frequency, the slope has been changed. So this is the corner frequency, omega is equal to 1 by tau. Actually, in Bode plot, there are two types of plots. One is the Bode plot of approximate plot, and another one is the exact plot. So using the straight lines, when we draw the Bode plot, then it is called the approximate plot or the asymptotic plot. Those plots are not correct because the name is the approximate plot and it is near the corner frequencies, and the exact plots can be obtained by doing the necessary correction and near the corner frequencies. So here when I have drawn this line, that means this is actually the approximate curve. So this is the Bode plot of first order factor, that is in the denominator. And next we will consider what will happen if the first order factor have the repeated poles, that is at minus 1 by tau or minus 1 by t. That means the transfer function will be 1 by 1 plus st whole to the power n. So if again it is multiplied by n, that means for the phase angle it will be minus of n into tan inverse omega t, and for the magnitude plot it will be m into 20 log 1 by root over of 1 plus omega square plus t square. So just like the previous example, we can easily find out the Bode plot of the first order factor when it is multiple. So let's take another example of Bode plot of first order factor when it is located at the numerator. So it is a simple 0 and its expression is gs is equal to 1 plus s tau. So when gs is equal to 1 plus s tau, in the same way we can find out the sinusoidal transfer function g of j omega, that is equal to root over of 1 plus omega square t square, and the magnitude in dB is expressed as 20 log root over of 1 plus omega square t square. And the phase angle that becomes tan inverse of omega into tau. Now here also there will be two cases when omega is less than tau or omega tau is less than 1. That is the omega tau part is negligible, only this part will be present and the magnitude is 0 dB. So at the lower frequency range when omega is less than 1 by tau, then the magnitude will be 0 dB. And in the same way we can find out the angle in the lower frequency range is 0 degree. Now we will consider the second case when omega t is greater than 1. Then when omega tau is greater than 1, then 1 will be negligible and the magnitude omega t is equal to 1, that means omega is equal to 1 by tau, the magnitude will be 1 by tau, at that magnitude will be 0 dB, because the formula becomes 20 log only omega t, because this one portion has been considered as the negligible. So it becomes 20 log omega t, and when omega t is equal to 1, so it becomes 0 dB. But when omega t is considered as 10, that means omega equal to 10 divided by t or tau, then the magnitude becomes 20 dB. So the slope will be 20 dB per decade. That means for omega t is less than 1, the magnitude plot is the horizontal line of the 0 magnitude for low frequency region, and for omega tau that is greater than 1, then the magnitude plot is the straight line with the slope of 20 dB per decade. And these two asymptotes meet at this corner frequency point at omega is equal to 1 by tau. So this one is the complete Bode plot, and this is the magnitude plot of the first order factor in numerator, and this one is the phase angle plot. And here the phase angle is 0 at 0.1 omega, and when the omega value is varying, at omega it becomes minus 45, and then it will be minus plus 90 dB. So here this is the parameter of the terms present in the open loop transfer function. Here we can see if we consider the constant term, then the slope is 0 dB per decade, magnitude becomes 20 log k, and the phase angle is 0 degree. For origin, 0 at origin it becomes plus 20 dB per decade, and the phase angle is 90 degree, magnitude is 20 log omega. And if there are multiple zeros at origin, then it will be multiplied by n, so its slope will be 20 into n, and it will be again multiplied by n, 20 into n into log omega, and this is also multiplied by n, that is angle will be 90 into n. So this one is the pole at origin, that means single pole at origin 1 by j omega. Here the slope will be minus 20 dB per decade. The magnitude will be minus 20 into log omega, whereas here it is minus 90 degree. So if there are multiple poles at origin, then again all the terms will be multiplied by n. So the slope becomes minus 20 into n, magnitude is minus 20 n log omega, and the phase angle is minus 90 n. In such way, we can find out for the simple 0 and simple pole also. For simple 0, the slope will be plus 20, whereas for the simple pole, the slope will be minus 20 dB per decade. And here also, for less than values omega by tau, the magnitude is 0 and then it is 20 log omega. Here it is 0 but then minus 20 log omega. That means sign is opposite in case of 0 and poles. And the degree it is 0 for the lower region, and for higher region it is plus 90 degree, whereas for the poles it is 0 for the lower region and minus 90 degree for the higher region. So this is the semi-log graph paper of 5 cycle. So this is 0.1 and then I have multiplied it by 10, so it becomes 1. That means from 0.1 to 1 there are 1 decade, and 1 to 10 is another decade, 10 to 100 is another decade, 100 to 1000 is another decade, and so on. And this is the reference line, 0 dB line, and the y-axis it is representing the magnitude in dB, and the x-axis it is the logarithmic scale, and the unit is radian per second, that means log of omega. And here I have considered that each box in this small box is 4 dB. So if it is 4 dB, then after 5 small boxes it is plus 20, then again after plus 5 boxes then it is plus 40, after 5 boxes it is 60 and 80, so on. In the lower part you can easily draw the minus 20, minus 40, minus 60, minus 80 dB. So this is the magnitude plot on semi-log graph paper, and in the next video we will discuss how to plot the magnitude of Bode plot in the semi-log graph paper. And before that, we have to find out how to draw the slope on a semi-log graph paper. So in this previous slide, I have discussed that the unit of the slope is dB per decade. So this is 0 dB, this is plus 20, this is plus 40, this is plus 60 and 80, and this one is minus 20. So if you are starting from this point, then it is minus 20 dB is starting point, then you have to draw the slope of plus 20 dB per decade. So plus means you have to go upward direction at 20 dB. So after 5 boxes you will reach 0. So it becomes 20 dB. The difference between minus 20 to 0 is 20 dB. So this one is plus 20 dB and then 1 decade. So from this one here it is omega equal to 0.1. Then you have to multiply this 0.1 with 10. Then we will go to 1. So if we join this starting point with this, then the slope is plus 20 dB per decade. So similarly, I have drawn the minus 20 dB per decade. That means if you are starting from here, then you have to go 20 dB in the downward direction and then 1 decade in the right hand side. Then you will join the line and the slope will be plus minus 20 dB per decade. Similarly, from any point you can draw this plus 20 or minus 20, plus 40, minus 40 and so on. So for simplicity, I have drawn from 20 lines, 20 dB. This is minus 20 dB per decade. So if we start from 40, then from any point, if you have to go downward by 40 dB, and so it is 40 dB and then 1 decade. So the slope will be minus 40 dB per decade. If you start from here, so you are going downward 60 dB and then 1 decade. So it is minus 60 dB per decade. So from any point you can draw any type of slope in this semi-log graph paper. And you have to remember that the unit of slope is dB per decade. So either you will go upward direction for the plus positive dB per decade, and for negative dB per decade you have to go downward. Then you represents actually 0.5, because if it is 0.1, then this 2 is 0.2, this 3 is 0.3, this 4 is 0.4, so on, and this is 0.9, then 1. So if you are starting from this 0.5 line, then you have to go one decade. That means this 0.5 will be multiplied by 10, so it becomes 5. So you have to go in the right hand side from 0.5 to 5. So it will be represent one decade. So in this way you can calculate the slope and you can